The focus in Shigley's example 16-3 is disc brakes. The question states two annular pads, Ri equals 3.875 inches, Ro equals 5.5 inches, subtend an angle of 108 degrees, have a coefficient of friction of 0.37, and are actuated by a pair of hydraulic cylinders 1.5 inches in diameter. The torque requirement is 13,000 pound-F inches. So that's the stopping torque. It says for uniform wear, find largest normal pressure, P sub A, the actuating force, the equivalent radius for the force, and the force location, and then D, the hydraulic pressure. Now we got some of the parameters, and it's important for us to visualize this problem. We'll draw our brake disc, put the x-axis here, put the y-axis here. Here's our brake disc. Let's just try to imagine it's uniform. And now we know from the problem that this is 108 degrees. If it's evenly distributed, we should have 36 degrees and 144 degrees. And the problem said our inside radius was 3.875. Our outside radius is 5.5 inches. This is a uniform wear case, and we're looking for the maximum pressure. So we'll go get our equation as it relates to maximum pressure. Now this is the equation for uniform wear, and uniform wear can be assumed when the brake discs are not brand new. It's a more conservative assumption than uniform pressure, and so this can be used even instead of uniform pressure for estimating the capabilities of new brakes, because we know that all brakes are going to age over time. Now we have to rearrange this for the maximum pressure, and now we have to plug in our numbers. Note that this is the maximum pressure for one pad. We're going to have two pads because we have one on each side, the inside and the outside of the brake disc. So that torque we had, we can divide that between the two pads. 13,000 divided by 2. We have 108 degrees. Convert that to radians. We have to take it times pi radians over 180 degrees. Coefficient of friction of 0.37. Inside radius 3.875. Outside radius of 5.5. Third minus 3.875. Let's crunch those numbers, and we get a final answer of 315.8 psi. Next, we're asked about the force for actuation. The force equals at delta theta, maximum pressure, times Ri times Ro minus Ri. It's going to be 108 degrees times pi over 180 degrees, once again, times that 315.8 pounds per square inch that we just calculated. Got to watch your units here. Make sure you stay in pounds and inch units. Times that 3.875 in a radius times the difference. Math that out, and you get 1,748 pounds of force. So now we've calculated the largest normal pressure. We've calculated the force. Thirdly, we need to calculate the RE. That's the equivalent radius. Equivalent radius is simple. The radius at which the friction force can be considered to be applied to cause the torque. So it's simply halfway between this inner radius and the outer radius. 3.875 plus 5.5 divided by 2. So that's 4.688 inches. Okay, so that was essentially a moment about an axis in and out of the page. Now this R bar is a little bit more challenging to understand, but it's not bad. R bar is just the moment around the x-axis. So you can think of it as this is the area that the force has to be applied on. So how far is basically, not exactly, but almost like how far is the average location from this x-axis. Okay, so the longer this brake pad gets, like let's say this brake pad went all the way around, it was 360 degrees, then there's no moment because the center of all that area is right here. But then as you shrink it down, this center keeps moving toward the center of the brake pad. And if you can imagine a brake pad that was only this big, if it was really small, then that would be almost the same as the average radius there, the one we just talked about, the one we just calculated, the equivalent radius. Okay, so the difference between the two, the equivalent radius is the moment about the in and out axis, the z-axis here. So that's the location of the force causing the torque. And then this R bar is moment about the x-axis, which is going to regulate how far from this x-axis the force has to be applied to actuate these brakes. And that equation relates to the equivalent radius by the ratio of cosine theta 1 minus cosine theta 2 over theta 2 minus theta 1 times the RE. Okay? And we have to use this 36 degrees and this 144 degrees for these cosines, because if we said 0 to 108, we're going to get a different answer if the area is all shifted over here. Our final answer is going to be much closer to the x-axis. So we have to use the 36 and the 144 to pull that force application radius further away from the x-axis. The denominator is just the difference, so I can use 108 degrees there, and that's the 4.688 inches. This has to be radians, and so that equals 4.024 inches. And the last question is, how much hydraulic pressure do we have to apply to get that force? And we know the hydraulic cylinder size on both sides is 1.5 inch diameter. So that hydraulic pressure needs to be the force we're applying, 3748 pounds force, divided by the hydraulic cylinder area. Don't forget to use the radius, which is half the diameter, so 0.75 inches squared, and that is 2,121 psi. So in Shigley's example 16-3 for disc brakes, we had this size of a disc brake with this amount of subtended angle from 36 to 144 degrees with 3.875 inch inner radius, 5.5 inch outer radius. We calculated the largest pressure, 315.8 psi. From that, we calculated the force that needs to be applied, 3,748 pounds force. Calculated the equivalent radius for where the friction force is applied, which is just the average radius between the inner and the outer. That was a 4.688 inches. We calculated the distance from the x-axis, that is the focal point of the moment or the force that we need to apply on that brake pad, and then we calculated the amount of hydraulic fluid pressure we need to apply that force given the size of the hydraulic cylinder. That's Shigley's example 16-3 disc brakes.